thank you. And except from the traditional thanks to the organizer, I also want to thank to my two prior speakers, Alain and Francois, who gave a part of my slides and made me possible to go faster through them. So this talk will actually be a combination of two talks that we're supposed to do, and but they are related, so I was able to make one presentation. And of course, all the world, or at least the astronomical world, hold its breath when Proxima b was discovered a couple of months ago, and there was a zoom of papers. But this is actually only one of many possible. And in this talk, the real subject is not Proxima b, it's only a good example, but all planets of its sort, M-stars, and I hope I will have time to go to the implication of this on the statistics of biotic stars in our neighborhood, which is the other part of my talk. So we have discovered many systems like this that have M-dwarf or K-dwarf in the middle, and therefore the habitable zone is smaller than what we have in our solar system. We have also seen already many times this figure, but this is different because I circled Proxima b, and also all the red dwarf, M-star and somewhat K-stars, Earth, and we see there is a number, not so many as Jupiter's, but this is our observing limitation right now. But in the habitable zone, there is a number of Earth-size planets around, and all of them around M-dwarf. This is a M-dwarf region. So this is very interesting to do this, and I was just thinking maybe we can do some simple model which will enable us to do a research along the parameter space of all possible things. So when we talk about life on planets of M-dwarfs, first of all, it's interesting because 70% of all stars are M-dwarfs. So statistically, we are more likely to find M-dwarf habitable planets. As we said, the habitable zone is small, and hence if they are in the habitable zone, they are close to their sun, host star, and they are likely to be gravitationally locked or nearly synchronous rotation, like Mercury and Venus actually also. Surface temperature distribution is a very interesting question. On this would the answer depend if this planet have or have not liquid water. And then another relevant question is, can a water-rich atmosphere survive or even emerge on the energetic early stellar evolutionary stages of M-dwarfs? They have an extended energetic path which may sweep away the atmosphere. And the answer to this is that there are simulations who show that this is possible for sufficiently massive planets and proto-atmosphere. So what is sufficiently, it's kind of fuzzy, but for particular situations, not too extreme, people have been shown that this was possible, and of course it is also possible to create a secondary atmosphere under certain conditions. So this is not an outrageous assumption. So this is a situation of a red dwarf locked planet. So here we have the host star. Of course, it's not to scale. In our terminology, we'll consider this the substellar point, which is almost facing the sun, a latitude of 90 degrees, like the pole, if you want. And then at 0 degrees, you have the terminator, which is the boundary between the constant day and constant night. And some people say it's interesting to see if there may be life exactly in this region. This is one possibility, but what I show is it is not necessarily only this region. Life may thrive on all or part of the planet, depending on the parameter space. So this is a 1D climate model which I put together. It's not 1D in the usual sense. The usual sense is the 1D is in the vertical direction. This is a latitudinal 1D model. So we are going from the pole to the terminator and to the other pole. And this is a very detailed slide, so let's start a little explaining. So we can write a very simple heat transfer equation. And here we have the radiation from the planet to space. So this is the usual sigma t to the fourth term. And this is some term related to the optical depths of the atmosphere, which is actually the greenhouse effect. It's an infrared optical depths, weighted, integrated, but so on. This term is the albedo. A is the albedo, 1 minus A. This is the stellar flux. And the stellar flux, the stellar radiative flux, depends, of course, on the latitude, but also on a parameter which I call F. It's the redistribution parameter. This says if the planet has a large atmosphere or ocean with jet streams and so on, there will be a redistribution on the face of the planet of the heat. So some of the heat that the substellar point gets will be transformed over the whole planet. And then I added, this is actually the new term that I added. This equation has been published several times. But this is a new term. This is an advective term, a local advective term. And while this equation you can solve analytically very easily, when you add this term, it becomes a second-order differential equation, which is also easy to solve numerically. And so there are two advective parameters. One is the global heat redistribution here, which I already mentioned, and B is the local heat advection coefficient, if you have turbulence or small-scale advection and so on. And there are two heating factors, which I'll show later, soon. One is the atmospheric heating, which is a combination of the albedo and the greenhouse effect. So this is the albedo term, and this is the albedo effect, the optical depths in the infrared of the atmosphere. And then you can define a modified heating factor, which takes into account all this, and also the radiation from the host star, and of course in a unitless form in scale to Earth's insolation. So all this have been already, people have spoken, so I don't have to redefine insolation and so on. So this is the first thing. This is also not very new. This is if you just solve without the advective term. And if you take Proxima B parameters, this is a relative flux to Earth 0.65, an albedo like albedo of Earth. Of course, we don't know the albedo, but that's why there's a question mark at 0.3. And this is for tau 0, so no greenhouse effect, but with the atmosphere. I mean, in the sense that there is a global redistribution. So the global redistribution parameter is here. It goes from 0, where there is no redistribution, then it is 0 degrees on the night side, to 1, when there is full redistribution, then it becomes isothermal, and everything in between. So here we have the maximum temperature, and it goes down like a sinus, the angle, and then it's isothermal on the night side. And if there is global redistribution, we just have a toy model which we have a isothermal night side, but warmer than 0 degrees. Okay, but this is also for no local advection. If you put in local advection, then the picture becomes more interesting. But first I have to say, just to show that you can treat 2D models where you have also the vertical structure. And what you can see from this, it's the greenhouse effect. This is at the top of the atmosphere, the temperature, equilibrium temperature, and the greenhouse effect increases the atmosphere at the surface. So we are interested in the greenhouse effect, and this is shown here for the same thing, but here we have the temperature for greenhouse effect, which is represented by this global heating factor A, mainly greenhouse effect in it, and global advection F, and local advection B. We took some, you can vary this between 0 and infinity, and this you can vary between 0 and 1, as we said before, and these are the profiles that you get. But this figure needs a little explanation because of its right vertical axis. So here there are various values of A, but you don't know what this A is actually, so I put it on the vertical axis together with typical values for the solar system terrestrial planets. So we have here A is 0.1. You see this is the naive water region between 100 and 0 degrees. So this is Mars, 0.3. Earth would be 1.1. So Earth is this curve, just a little above this curve. Earth would be a little here. So you see there is a large region of possible, if Earth would be locked, of course, of a possible temperature for water. Mars would be just on the limit. And Mercury would be here, but this doesn't say that Mercury has a lot of water because it doesn't have an atmosphere and it doesn't have water, but it could have. And the Venus would be up here, and this dash here, so even above this curve of 10. So Venus would be something like this. Okay, so let's go on. We can do this a little more generalize the thing. We can ask, what would be the same temperature limits between the maximum temperature? So these are the maximum temperature of the highest temperature point on a locked planet, and this would be the minimum temperature on the opposite side. And this, we already know the parameter f. It goes from 0 to 1. This is a logarithmic scale. So if it's 1, it's isothermal. So the minimum and the maximum are the same. And these colors are for different A's, so 0.1, 1, and 10. So you remember Venus is about 30, Mars is about 0.3, Earth is smack 1. So this is for F. And we see a large fraction of this region passes through the possible liquid water temperature. But what about B? If we vary B, we get similar diagram, but somewhat different. So this is for a particular value of F. And we see that also if B becomes very large, it also becomes isothermal. But this is because the local distribution of heat becomes so strong that the second derivative in the equation is becoming global. It is transporting enough heat from the substellar point to the opposite pole to become global. And then F is not important if B is large. Anyway, let's go on. We can generalize even more and put a Proxima B into the picture. So here we have the same x-axis with F. This part is for F and this part is for B, logarithmic scale. But this one is the AP. Remember, AP is the heating parameter independent of the insolation. So just the atmospheric properties, namely the albedo and the greenhouse effect. The greenhouse effect can be related to the optical depth in the infrared, so here it is in these units, assuming a particular albedo. So what we see here in this figure, this is, in my opinion, the most important figure of this talk, of this work, is that, here we also have this, the solar terrestrial planets, that is Venus, Earth, Mars, and Mercury. So here we have for F, for a locked planet, of course, with F going from 0 to 1, we see that, and a dashed line is for Proxima B. For we know the distance from its sun, so we know its insolation. We don't know its atmosphere, so we don't know AP and we don't know F. But anywhere we put it, we see that Proxima B would have a large enough region where this this is a T minimum and this is T maximum in the parameter space, a large enough region where it could have liquid water. And the same thing for B. So 5 minutes, I will do it, I hope. So this is another question, an interesting question about the possibility of oxygenic photosynthesis on habitable planets. I will not reside alone, but I'll just say that if you have a moist atmosphere, this is the condition for this are moist atmosphere, oceans or vapor, and light. Of course, then it cannot happen on the night side. So the liquid water should be on the lighted side unless you have special conditions. And the M-scar spectrum is enough to have enough energy in the visible, so it could be Earth-type oxygenic photosynthesis. You don't need to go to exotic infrared photosynthesis. And the earthly oxygenic photosynthesis signature is an oxygen ozone line. So the question is, can it be biotic? And I will not go into this, we don't have time, so I'll just show this picture. Oops, no. Yeah, from the General Assembly in Hawaii, they had this nice NASA poster of Kepler, which is an M-dwarf planet, and he said the neighbor's lawn would always look redder. So I put a note here, which was then removed by the organizer. The grass on planets on red dwarf may well be as green as on Earth. Well, let's go to the final point of this lecture. Biotic abundance of the distance of our nearest biotic neighbors. Well, these are several papers I published over the years. But the main point here is that if it depends on a yet unknown biotic probability. This is a parameter in the Drake equation which says what is a probability that biotic life will emerge on inhabitable planets. And you see, this is, you can calculate the distance. Here it's in light years as a function of FB, and this is assuming with M stars. If you exclude the M stars, so this line goes way up, and so it's a good reason to explore M stars. And this is, I'll skip this. This is the equation that one gets. It's very simple consideration. The distance to the nearest neighbor would be a FB to the power of 1/3 and 10 light years if FB is 1. Now, you can do the same thing before and after Kepler. And you see here that these were possible lines with different parameters for the planetary distribution, like Earth and habitable and so on. This was the possibilities before and even more. Now Kepler constrained the thing to be along this line, and if we assume that FB is in a certain range between 1 and 0.1, it will be this thing. Between 1 and 0.003, it will be this ellipse. So we are getting to the end. This is showing that many planets indeed were found to be small planet Earth size. And the abundance of life-suitable planets of around red dwarfs was really strengthened by the Kepler work. Everybody knows this, so I won't go into this. So we can, we can just do this summary picture that differentiates 3 kinds of population. If you assume that life is possible only on a solar type and the habitable zone planets are rare, there is a range in the Kepler results as well, then you get this green, the same distance to the nearest biotic neighbor. This is FB, log FB, so this line. If you consider a larger habitable zone, then you get this thing. And if you add red dwarf into the mixture, you get this low blue line. And so let's skip this, just put the conclusion. Oh, this is important. I did some naive calculation. What was James Webb combined with TESS? What sample could it analyze to have this really enough transiting planets And this is, again, for this abundance parameter, 1.1 and 0.01. And this is the number, the distance that it would see. So if James Webb, for example, could look to about 30 parsecs, recognize biosignatures, then you would have, in this scenario, you would have some 100 planets at this distance and so on. So you can put on, these conclusions, and I really should finish, so I'll let you read the conclusions yourself. Thank you.